shall discuss about finite element method. There is a methods to analyze the stress distributions and the strains structures when the loaded structure is loaded. Is in various engineering applications. It's mechanical, aerospace, civil engineering, automobile engineering, anywhere it is applied. It is mainly used for structural analysis, static dynamics, linear and nonlinear, thermal and fluid flows, electromagnetics, geomechanics, biomechanics. These examples which I discussed, little bit examples is given: conduction, heat transfer, sulfur temperature distribution throughout the body with known boundary conditions and material properties. Fluid mechanics problems range from the steady, incompressible flow to complex mixed compressible flow in various cases. The acoustics use finite elements and boundary element numerical methods. Electromagnetic solutions for magnetic field strength. The insight into design of electromagnetic devices. Capabilities include the fluid structure interactions, biomechanics, structural analysis, blood flow in blood vessels, finite element methods. Numerical method of solving is a numerical method. System of governing equation over the domain of continuous physical system. Method applies many fields of science and engineering. Engineering use field of continuum mechanics, theory of elasticity, provide the governing equations which is solved by a finite element. Numerical method is used in order to have a solution easy. Most engineering problems, solution of governing differential equations, you can see as in the case of a tapered beam, is displacement is satisfying the equations du by dx plus p by ax e equal to 0 at the fixed edge, which is marked as lines are marked, this is fixed end, and where u0 is equal to 0, and unknown displacement and various points are found by the equations. You can see for the beam, this governing equations of deflection is given d port w by dx port x by ei equal to 0. At the 0, dwx is the slope, and both deflection and slopes are 0 at the fixed end, and this is unknown displacement is w, which is solved by the finite element. Rate transfers, torsion of shafts, rotational flow, seepage through porous media. These are the equations. You can see del of del x, del phi by del x. This is the potential function, you can say kx, del phi by del y, ky, del phi by del z, kz, differentiated over z plus q is equal to 0. Boundary condition, particular surface, this known functions of phi is given, and unknown function phi is to be solved inside the domain. Solution is tedious, sometimes impossible, therefore finite element will go for finite element. Complex geometry, boundary conditions, loading conditions and material. The geometry is complex, you cannot have the proper solution, exact solution. Boundary conditions also have various typical boundary conditions. Loading conditions and materials have got different type of material at different positions, as in geomechanics and soil mechanics you can observe. You can see here this boundary is very undulated. You don't have any particular functions for the boundary, geometrical function to describe, hence we go for the finite element method. And here there is discontinuity inside the continuum, and the boundary conditions are various at various points. Sometimes displacement boundary conditions, there is the pin and fixed positions, and there is loading condition at the surface, and there is discontinuity also in set, and we cannot solve it as a continuous function. Hence we have to go for finite element method. And this undulated beam also, when the loading is also different at different points, has no particular functions, and we can go for finite element method. And the solution, the domain is divided into these elements, and this process is carried out.